In this lesson, so we're on what page are we on? Page 12 of your thermochemistry package. I've opened this in Word. If you look at if you're looking at everything online, I don't know what happened, but it turned this picture around in the viewing of the online thing, and I don't know why, and I don't know how to fix it other than uploading a PDF. So I've just gone into the Word document, and we're going to talk about, now that we know how to calculate enthalpy, we're going to talk about different ways that we can represent enthalpy in our communications. So sometimes, it's going to be communication where you're reading something, so you have to understand by reading or looking at something, whether what kind of change in enthalpy has gone on, whether it's endothermic or exothermic. So we have different ways of making communications about enthalpy, and some of them involve writing chemical equations, and some of them involve looking at graphs. Oh, I just highlighted that graph. I didn't know you could highlight a graph like that. That's kind of cool. And there we go. Okay. So as part of the course, right, you're going to have to learn how to read things that are about enthalpy and interpret them, and how to write things about enthalpy. So recall that enthalpy, it's funny because this the course goes so fast that that we just learned about enthalpy, but these notes assume that we learned about enthalpy like last week. Recall that enthalpy is a measure of the absolute energy present in a given system. Okay, all of the energies of the molecules, whether they are kinetic or potential, right? They're in enthalpy together. So enthalpy is the sum of the intrinsic energy in the particles that make up a system. The intrinsic means within. Intrinsic energy in the particles that make up a system. Okay, and that includes both kinetic and potential energy. However, we are more interested in knowing the change in enthalpy in a system, whether when a physical or chemical change occurs. Right? So that's what we're interested about learning how to communicate. Enthalpy is represented by the symbol H, right? And the change in enthalpy is represented by the symbol, not box H, but delta H. Don't want to get rid of that. Okay. So I'm going to replace this symbol with the real symbol that it's supposed to be, the delta. If you ever have to, as in your homework or in an assignment, if you have to put a delta in a Word document, you go to the insert ribbon on Word and you go to symbol. Should be right there at the end. And usually it's one of the symbols, one of the symbols listed. If not, you have to kind of look it up. Anyway, the change in enthalpy is represented as delta H. In measuring enthalpy, we make the assumption, right? So regular old enthalpy, H. The change in enthalpy, delta H. Right? Let's make a distinction there. Okay. So enthalpy is just H. The change in enthalpy Really, give me the C. There we go. Is delta H. There we go. All right. In measuring enthalpy, we make the assumption that the change in enthalpy of a system. Remember how we talked about assumptions as one of the homework questions. We were making the assumption that the change in enthalpy of a system is equal to the heat gained or lost by the surroundings, right? So that is one of the assumptions that we make for calorimetry. The change in the enthalpy of a system is equal to the heat gained or lost by the surroundings. So 3 assumptions, okay? Number 1, the conservation of energy, meaning that no energy is created or destroyed when you're doing reactions, and so the energy given off by one thing is equal to the energy absorbed by the other thing. The change in the enthalpy of a system is equal to the change of in the change of the surroundings. So that's number 2, right? Number 1 is the conservation of energy. Number 2 is that statement. And then number 3 is that the calorimeter is a perfectly isolated system. Anyway, so we know this equation, delta H equals Q, right? Delta H, we should say delta H system is equal to Q of the surroundings. So it says consider the chemical equation little a, big A. So the little a, right, the small letters here are equal to coefficients. And the large letters are the chemical formulas of the reactants and the products. Okay, so we have like three methanes plus 5 oxygens make however many carbon dioxides and however many waters, right? That's the idea here. Okay, so the small a's represent how many of each substance there are, how many molecules, and the large letters are where the chemical formulas would go. So this reaction could be either exothermic or endothermic, right? The heat released or absorbed is referred to the heat of reaction. Because this is a chemical reaction, okay, and we don't know what type of chemical reaction it is, the Q is the heat of reaction. The enthalpy change for the system in which this reaction occurs is equal to the heat of reaction. So enthalpy, right, equals heat, right? That's going back to this equation again. Enthalpy is equal to heat, okay? So if this reaction is exothermic, then we consider the heat of reaction to be a product, right? If something is exothermic, it gives off heat. So our heat is given off as a product, right? But if it's endothermic, the heat is absorbed as a reactant, right? So if a reaction is endothermic, it requires heat to take place. So heat becomes a reactant, just like we need the chemicals, the starting chemicals to take place. Okay, so if the reaction is exothermic, Q, you can list Q as a product. If the reaction is endothermic, you list Q as a reactant. And you'll notice, right, I need to point out the signs here. Okay, when we write something as part of a chemical reaction, the sign of it is always positive, right? We're used to writing about enthalpy changes, exothermic enthalpy changes as negative, and endothermic enthalpy changes as positive. But when you put it as a reactant or a product, that gives the same information as the sign did, right? So we're not going to put, you know, the Q that's from the exothermic reaction, it's not going to be negative in this situation because we know that it's written after the arrow. So we know that whatever number goes in for Q, right, is negative. Yeah, and then if we see it written as a reactant, we know that it's positive. So down here, I have a summary of differences between exothermic and endothermic reactions. So remember, exothermic reactions, the system loses heat to its surroundings. The enthalpy of the system will decrease, right? Because energy is going out of the chemicals that we're studying and into whatever's surrounding them. The heat of reaction, Q, is negative. And I have a feeling that something needs to be written here. The enthalpy of the system, is it on the next page? Oh, so we're going to see graph on next page. Actually, let's write the little bit of enthalpy of the system is in an, what is this, exothermic reaction at the top? Yes. We can write that it's written as a product. And we can write here that it's written as a reactant. There we go. Okay, so that's the summary of what we've learned so far about exothermic reactions and endothermic reactions. On the next page, we're going to take a look at the graphs, what an exothermic graph looks like compared to an endothermic graph, right? And this is why I should have taught rates of reaction after this, because it's going to look very familiar to you. Right? We've seen these graphs before in our rates of reaction. We have energy or enthalpy, right? Up on the left-hand side, and we have time down across the bottom, right? So remember, as over time, we go from reactants to products. Let's see if I can write on this in Word. This could be kind of sketchy. Sketchy. Draw. Okay, so reactants. Let me do an E. No, it doesn't let me right there. Reactants. We tried. Our reactants are written on the left-hand side, right? So this line, this horizontal line that you see at the beginning is indicating just the energy of the reactants. Okay. The line to, sorry, the line on the left is the reactants, the horizontal line on the right is the products, and the part where it goes from one to another, right, the slanty line represents where it's changing, right? So we can see here we have an exothermic system. We start off with reactants that are high energy. We end with products that are lower energy. And this line represents the energy decreasing, right? It's decreasing. So it's leaving, it's going out of the chemicals that we're looking at, right? So you can see here what that looks like, right? So you can see it in a graph and you can see it in an equation. Okay, here we have an endothermic change where we have a low energy reactants and high energy products. And you can see that the energy goes up over time. So it must be absorbing energy from somewhere, and that somewhere is the surroundings. Okay, so in summary, there are 4 ways of communicating the enthalpy change of a physical, chemical, or nuclear change. We could just simply state the enthalpy change, and then we have delta H equals, right, some number. If the number is negative, we know that it is an exothermic reaction. If the number is positive, we know it's an endothermic reaction. The next way that we can talk about enthalpy is to write the reaction itself. Okay, and then list the enthalpy beside it. Right? So we can tell that again, right? So all of these are going to be about the same equation. So we can just talk about the enthalpy without writing the chemical reaction. We can talk about the enthalpy by putting it beside the chemical reaction. We can talk about the enthalpy by putting it into the chemical reaction. So notice the difference between 2 and 3. In 2, we just wrote the reaction and we didn't put a plus in between the products and the enthalpy. We didn't put a plus there, okay? We just listed the enthalpy beside it. So you can see the delta H is still there, and you can see that the enthalpy here still has the negative sign. But when we write it as a part of the chemical reaction, okay, there will not be a negative sign. You know it's exothermic if the enthalpy is written on the right-hand side, and you know if it's endothermic if the enthalpy change is written on the left-hand side, right? And finally, we can make a graph. If you make a graph of an exothermic reaction, the products will be lower than the reactants. Of course, if it was an endothermic reaction, the products would be higher than the reactants, right? So that's the way you can tell from the graph, right? High to low is exothermic, low to high is endothermic. Again, we have some practice questions here. The practice questions are pretty easy compared to the other ones. Okay, it says communicate the enthalpy change using the 4 methods for each of the following chemical reactions. So you're going to write about the enthalpy of the formation of acetylene from solid carbon and gaseous hydrogen 4 times, right? You're going to write the enthalpy on its own, right? You're going to write it next to a chemical equation, which means you're going to have to come up with the chemical equation for the formation of acetylene. Acetylene is another word for, I believe, let me just make sure, because it's one of those old terms. Yeah, acetylene is ethine, right? So the formation of ethine from solid carbon and gaseous hydrogen. That will give you some practice writing chemical equations, or if you feel that's too much for you, you can actually Google formation of acetylene, and it will give you you know, the chemical reaction, right? It'll give you the equation. But I highly recommend that you test your brain out, and if you have some memory of writing chemical reactions, chemical equations, that you try to test your brain out. The decomposition of aluminum oxide. So For each one of these, right, we're going to write the enthalpy. We're going to write the enthalpy next to the equation. We're going to write the enthalpy as part of the equation, and you're going to draw a graph. And then it says, for each of the following chemical reactions, determine the molar enthalpy per mole of oxygen. This is also easy. So all you're going to do is you're going to take the enthalpy. So this enthalpy is the enthalpy for the whole reaction. So all you have to do is take the enthalpy for the reaction and divide by the number of moles of oxygen written in the chemical equation. So the first chemical equation only has 1 mole of oxygen, so you would divide by 1, you'd get the same number. The second chemical equation has 7 moles of oxygen, so you would take the enthalpy number and you would divide by 7, right? So that's pretty easy. The neutralization of a strong acid and a strong base is an exothermic process. Consider the following. So it gives you a communication, right? Where enthalpy is part of the chemical equation. It asks you what is the enthalpy per mole of sulfuric acid. So you would have to divide the overall enthalpy by the number of moles of sulfuric acid in that question. What is the enthalpy per mole of sodium hydroxide? And then it says, if 25 grams of sodium hydroxide was neutralized by excess sulfuric acid, how much energy would be released? So you can, right? So here we have a mass of sodium hydroxide, and we just calculated the molar enthalpy of sodium hydroxide, right? So you can have practice converting the mass into moles, and then multiplying by the molar enthalpy for sodium hydroxide. If the solution of the neutralization took place in was 1 liter of water and had an initial temperature of 21 degrees Celsius, what would the temperature become? So that last question is going to test if you still know about calorimetry, but mostly the questions there are fairly straightforward. They don't seem to have any answers, so I'll work on that for you. Now we get to latent heat. This is the last little bit for today. So in general, we associate a change in thermal energy with a change in temperature, right? The higher the temperature, the more energy is in our system or our chemicals. And this is because the gain or loss of energy results in a change of the average kinetic energy of the particles of a system. This is because the gain or loss of energy results in a change in the average kinetic energy of the particles in the system. So when something increases in temperature, the particles gain speed. However, this is not always the case. When a substance undergoes a phase change, right? So that's a change in state. The energy gained or lost by the system energy is gained or lost by the system without a change in temperature. And you can test this if you have at home. What do you need? You need a thermometer and you need the ability to make ice, right? So what you can do is we'll take a look at what happens here. There's another gizmo. We're not doing the gizmo, but it looks at what happens. So if I go to gizmos and I look at for phase change, I can add this. Is it part of your thing? I don't know. Hold on. Let's see if it's part of our list of gizmos that we have access to. No, but I can add it. So this will be available if you want to take a look at it. If you set up, so we can take a look at this. I've made this water negative 35 degrees Celsius, and you'll notice that when I made it less than 0, when it's at 0, you can see it's sort of dark, and when it's at minus 15, you can see it's sort of light, right? That's because at 0 degrees Celsius, water goes from a liquid to a solid. So by taking this down to like negative 25 degrees Celsius, I have turned it into ice. Okay. And so I can add energy to this water, and I can watch what happens. So you can see that when I added energy, the little fire started in front of beneath the water. And right down here is a little stir bar. That's gonna, once this turns into a liquid, that's gonna start spinning, and it's gonna just distribute the energy, equally amongst the water. So now, actually, hold on. This is going a little bit too fast. Okay. There. Okay, so I'm going to start it again. And it's going to start at minus 25 degrees Celsius, right? Because that's what I set the water to. And you're going to see initially the temperature is going to start to increase from negative 25 to 0 while the ice is melting. Or sorry, no, that shows that the ice is heating up. Okay, so it's going to start off at negative 25, and it's going to quickly start rising from negative 25 until 0. And that's going to be the ice heating up, right? So ice is water at 0 degrees Celsius or less, right? But there, we know that there's negative degrees Celsius. So you can make the ice as about as cold as you like, right? Temperatures go down to about minus 273 degrees Celsius, right? That's the coldest anything that anything can be. So you'll notice that it'll go from minus 25 to 0, and then this ice will change into water. It'll like go sort of that darker blue color. But while it's changing, what do I want to say? While it's changing, there, we'll show the molecules too. While it's changing from ice to water, you'll see the temperature stays at 0 degrees Celsius. Okay, so as the ice is heating up at first, watch the particles, okay, and you'll see the particles start to move faster in the ice, right? As the temperature increases, these particles should move faster. Then the temperature will hold at 0, and this ice will change to water, and the temperature will not increase again until all of the ice is melted, right? So you can, if you have a thermometer, you can have a setup like this at home. It doesn't have to be over a flame, right? It just it speeds it up if it's over a flame. So if you have a pot of water and you can make some ice, put some ice in the water and let everything sort of come to the same temperature, and it'll be some very, very cold temperature. And if you leave the thermometer in the pot and you turn the heat on, right? If the temperature is lower than 0, the temperature will increase until it gets to 0. and then it won't increase anymore until the ice is melted. Okay, so we'll watch what happens, and while we're watching what happens, it will show a graph of the temperature over time. Okay, so you can get an idea of what's happening here. So I'm gonna switch over to here. So this graph will show you, it's a graph of temperature versus time. So as this goes on, right, it will show you where the temperature is. So we'll watch we'll watch this happen now. Okay, so you can see the temperature is rising. Okay, and it gets to 0, and you can see the ice starts changing to water. And when it changes to water, you'll notice that the molecules are able to move more, right? So that energy is going to making those molecules move more and not raising the temperature. Okay, so until all of these molecules become water, now they're all water. Okay, and you can see the temperature is rising again, right? And it's going to rise until it hits 100 degrees Celsius. So right now, while the temperature is rising, um, you know, the molecules are starting to move faster and faster, right? And they'll move until it, so it's the energy that's being added is changing the kinetic energy of the molecules. And then when it hits 100, it's going to change the space between molecules. And now you can see that it's starting to bubble. So these molecules are changing from a liquid to a gas. And while they're doing that, the temperature stays at 100 degrees Celsius, right? So you can see sort of we're making like little plateaus while the water is undergoing a phase change. So, right, while we're in the slanty parts, it's a substance heating up. So we started with ice heating up, okay? And then the ice started to turn into a liquid, right? That's a phase change. And while we were watching the ice turn into liquid, the temperature stayed the same. But once everything was all water, liquid water, the temperature started rising again, right? So the heat that is being added during the plateau is going to the change of state, the phase change. And then during the slanty parts, it's causing the kinetic energy of the particles to rise. It's causing them to move faster, right? And then when it plateaus again, there's another phase change, right? So it's increasing the space between the molecules, and it's increasing the space between the molecules, and it's overcoming the forces that hold the molecules together. Okay, and this will continue to go flat until we're out of water. Boy, I wish I added less water. Just waiting for that to happen. Oh, I don't think it'll go up again afterwards, right? Because it's measuring the water down here and not the steam up here. So that's fine. But if it was measuring the steam, it would as soon as all of the water had turned into steam, we would see the temperature of the steam go up again. So right. So when we add heat to a system, it can do one of two things. Okay, it can increase the kinetic energy of the particles, which results in a change in temperature, or it can start weakening the intermolecular forces, in which case we have a case of latent heat. So latent heat is what happens when there is a phase change, and the energy being absorbed is not being used to increase the temperature, but break the intermolecular forces and turn a solid into a liquid or a liquid into a gas. Okay, so you can see on this graph here, I have the same sort of graph that from the gizmo. And anytime it's flat, okay, we have a latent heat. So we have the latent heat HV, the latent heat of vaporization, which is when we go from a liquid to a gas. And we have the latent heat of fusion. And the heat of fusion is when we go from a solid to a liquid. Okay, so we start off with ice, right? So this ice represents between here and here. Okay, this first slanty bit is all ice. And during the slanty bit, in this particular graph, ice is heated. Oh, we have something that we have to talk about. We have to talk about the temperature on this graph because the temperature here is in degrees Kelvin, which is the standard way we measure temperature in science. So the metric for temperature is Kelvin, and Kelvin and Celsius are related, but they have different starting points. So if this were in degrees Celsius, you know that I'm going to try to right here. You know that water or ice melts at 0 degrees Celsius, right? So 0 degrees Celsius is equal to 273 degrees Kelvin. Okay, which means that 0 degrees Kelvin is equal to negative 273 degrees Celsius. And you can't that is a temperature called absolute zero. It's called absolute zero because we can't have matter. Matter can't get any colder than that, right? So absolute zero or negative 273 degrees Celsius is when particles stop moving. There's no energy in the particles. There's no kinetic energy whatsoever. So that's the coldest that a substance can get. Okay, so we have 0 degrees Kelvin or negative 273 Celsius is the coldest anything can be, and everything is solid at that temperature. Okay, so you can get water to negative 273 degrees Celsius, and then you can heat it up, right? And it'll stay ice, but get warmer and warmer until 0 degrees Celsius. And that is the melting point of water. Okay, so then we get a plateau. And when I say plateau, I mean a horizontal line, right? So the word plateau, right, refers to this, the horizontal line, okay, where the temperature is not changing. Okay, at that point, all of the energy that you add to the water is going to changing it from ice to liquid water. So at that point, you're going to have a mixture of ice and water. And you're going to start with more ice, right? And it's going to lessen over time and you get more water. Okay. When everything is water, the temperature will start rising again. Okay, so we'll get this horizontal line. Now everything is water, and the water is going to increase in temperature, which means the particles are going to go faster, right? So we have all liquid during this part. And it will be all liquid until 100 degrees Celsius. Which is 373 degrees Kelvin, right? So the amount that we add to go from here to here is the same, right? To go from 0 Celsius to 100 Celsius, we add 100. And to go from 273 Kelvin, right, we would add 100 and we would get to 373 degree Kelvin. So the amount of increase for Celsius and Kelvin are the same. It's just where 0 is. It's different. So at 100 degrees Celsius, which is the boiling point of water, you'll see another plateau, another horizontal line, right? And there, the energy is not going into how fast the particles are moving, but it's going into weakening the intermolecular forces again. So I think this arrow is a little bit off. We shouldn't have it here. Here, right? Is the during the plateau part is where the intermolecular forces are changing, right? Being weakened. I think what this is trying to tell us is that the intermolecular forces are stronger in a solid than a liquid. Okay. That's why it's written the way it is. So you don't have to like make the changes that I did. Okay. Once all of the water has boiled away, okay, the temperature of the steam, if we measure it, will continue to increase. So if you get burned by hot water, the highest the temperature can be is 100 degrees Celsius, give or take. There is another factor that it could increase the temperature of water, and that's the air pressure. So like if you cook at a high altitude, the temperature that water boils at is actually a little bit different. But that's beyond the scope of this course. But if you get burned by steam, steam can go up and up forever, right? So you would actually be burned at a higher temperature if you're burned by steam than 100 degrees Celsius. It could be 200 degrees Celsius. It could be 5,000 degrees Celsius, right? Once water is a vapor, it will continue to increase in temperature and can get very high temperature. So when things are slanted, they're only one phase, right? That steam slanty line, we know everything is a gas. And then when things are on the plateau, it's a mixture of two phases. It's a mixture of the substance in two states. Okay. But the point is, right, when it plateaus, it's because the energy is going into changing states, and we have something called a latent heat of vaporization or latent heat of fusion. So it says the amount of energy required to melt or freeze a given mass of substance is referred to as the enthalpy of fusion, and the amount of energy required to vaporize or condense a given mass of substance is referred to the enthalpy of vaporization. Okay, so these amounts are the same whether you're melting or freezing something. It's just the sign on them, whether the heat is absorbed or released, that will change. So since the temperature is constant, the amount of energy gained or lost by a system undergoing a phase change is equal to the enthalpy times the mass of the system. So we can have, this would be the specific enthalpy, so the specific latent heat of fusion or the specific latent heat of vaporization. There is, of course, a molar equivalent as well, but those would be different numbers. So we have some practice questions here, and it says practice questions, see reference tables from the previous module. Determine how much energy would be required to evaporate 1 gram of water. So in the previous section on page 9, okay, we have the molar heat of fusion and the molar heat of vaporization, right? So we can use these to determine how much energy is required to melt or freeze something or to condense or vaporize something, right? So it's using this chart, you're going to look up the substance and you're going to look up whether we need fusion or vaporization, okay? This is measured in kilojoules per mole. So I think they're giving us grams here. So you're first going to have to convert grams to moles and then multiply by the correct value from that table. And it says if you had this glass of water at 21 degrees Celsius, how much energy would be required to bring it to a boil and then completely vaporize the water. So you're going to do two calculations here and you're going to add them, right? The first calculation, so we have to figure out where we are on this graph, okay? So 21 degrees Celsius, we're at a part where we have to bring water from 21 degrees Celsius to 100 degrees Celsius, and then we have to evaporate it, right? So we have to do two calculations, okay? One calculation, so when you're doing calculations here, if you're working on a slant, if you're raising the temperature, you're going to use a Q equals MC delta T formula because you're changing the temperature, right? So anywhere there is a slanted line, if you want to increase it from 21 degrees to 100 degrees, right? You would find the mass of water. You would find the specific heat capacity of water, which is on like page 7 or something of our notes, like way back, that blue chart, right? Come on now. We use the air right here on page, what page is it? Was I close? Page 4. So on page 4, you have the specific heat capacities. So when you're doing the heat calculation for something increasing in temperature, you're going to use that and the Q equals MCT delta T formula. But when it's plateauing, okay, you are going to use the delta H equals N times delta H molar, right? So we would use this first and we would use the second, and then we would add them together to get our answer. So you are going to definitely use this graph, and you are going to use the charts on page 4 and page 9, question mark, 10. All right, so you're gonna use the this chart here and the one on page 4 to supply you with your delta H's and your C's. You might also need this table here. This table here has some boiling points. So not everything is water, right? So this is showing you different substances, and they're showing you their boiling points. Okay, and it's showing you how many kilojoules per mole or how many kilojoules per gram, or sorry, per kilogram. The substance makes when it turns into a gas, right? So we have to figure out some of these things. So it says the enthalpy of fusion required to okay, whatever. I'm trying to think. Oh, it has water here. I think most of the questions involve water, but if they involve another substance, you can look it up in this table, is what I'm trying to get out. So you can use the previous tables, or you can use the table here, and everything should work out the same because they should have the same values. Okay, so we have the answers, so you can check your calculations, and that's sort of it for today. So lots to do. You have the gizmo to do, and you have this to practice with. Tomorrow we are going to have our last 2 lessons in thermochemistry, and then we're gonna have a work period to help you get everything done. And so you can ask questions about the math if you're having some difficulties. But that's it for the lesson today. I hope that wasn't too difficult for you. If you are having difficulty with the moles to mass calculations, please look at the resources I've posted for you about them. And we'll see you in the next lesson. Oh,